to calculate the number of cycles. So from this point E, we have drawn a line which is parallel to x-axis up to the failure line AB, that is intersecting at point F. From point F, we have dropped a line which is just intersecting x-axis at a location. Corresponding to that, we can get the life in number of revolutions. So this will be equal to CD. This CD is equal to EF. So as we have discussed in the morning session, by using similar triangles, you calculate EF, that EF equals to CD. Then by equating that with life log 10 of n, we can have the number of cycles. So we are calculating fatigue life of the shaft from this particular figure. EF is EF by what it is, BD or DB is equals to AE by AD. So we are taken that from that EF is equals to, we are getting the value as 1.2030. So log 10 n equals to 3 plus this EF. 3 plus this EF. Log 10 n equals to 3 plus EF. That is nothing but 4.2030. So from that, we are getting the number of cycles as 15,958.79 cycles. So almost all the problems are very, very similar. If they have given stress, we are calculating life. If they have given life, we are calculating stress. Go for next problem. A cantilever beam made of cold drawn steel 20C8 with ultimate strength 540 Newton per mm square is subjected to a completely reversal load of 1000 Newton. A completely reversal load of 1000 Newton as shown in figure. The notch sensitivity factor at the fillets can be taken as 0.85, and expected reliability is 90%. Determine diameter D of the beam for a life of 10,000 cycles. Take surface factor as 0.78 and theoretical stress concentration factor as 1.35. So this is the problem given. Again, this is the cantilever beam with circular cross section with two diameters. Here it is 1.5D, here it is D. So certainly the failure will be occurred in a portion where we have lesser diameter. So we are considering this is the failure zone. Wherever we have the junction for larger and smaller diameter, that is considered as failure zone. So here we are considering that particular one. So as usual, we will solve this particular problem by drawing SN diagram. In order to draw this SN diagram, we need the data. So first we are going for theoretical endurance limit is 50% of ultimate strength, that is 270 Newton per mm square. Then we are calculating, this is not 30 mm diameter. Here we are considering the size factor as 0.85. This is not with 30 mm diameter. We need to calculate diameter of the shaft. We are considering, assuming that diameter is in between 7.5 and 50 mm. We are considering the size factor as 0.85. And reliability is, for 90% reliability, the reliability factor is 0.897. And fatigue stress concentration factor is 1 plus Q into KT minus 1. Already they have given KT and they have given notch sensitivity. So from those two, we are calculating fatigue stress concentration factor, that is 1 plus Q into KT minus 1, which is nothing but 1.2975. Then we are calculating the modifying factor KD is equals to 1 by KF, that is 0.771. Then we are calculating corrected endurance strength. Sigma E is equals to sigma E dash into size factor into surface factor into reliability factor into modifying factor. So by introducing all these factors, we got endurance as 123.8 Newton per mm square. Now we need to construct the diagram, SN diagram. So first you finish it and you draw SN diagram. Let us verify it. You try to draw the SN diagram. You calculate all these values, and for SN diagram you need coordinates of A, coordinates of B. You know what are the coordinates of A and what are the coordinates of B. Then they have given 10,000 cycles. With respect to the 10,000 cycles, you calculate the stress. After calculating the stress by equating that stress with bending stress, you can have diameter of the shaft or cantilever beam. First, you calculate all these values and verify them. So for SN diagram, 90% of ultimate strength, that is 486. Log chain of that value, 2.6866. Then log chain of endurance strength, 2.0927. We need to calculate fatigue or diameter corresponding to 10,000 cycles. So log chain of 10,000 is 4. Now we are constructing a SN diagram. For point A, 2 points are, one is 90% of ultimate strength is 2.6866 and number of cycles are 1000, so 3. These are the point coordinates with respect to point A. Corresponding to point B, endurance strength and 10 power 6 cycles. This is point B. Joined A and B, which is the criteria of failure. Now we need to get the diameter corresponding to 10,000 cycles. So log 10,000 is 4. This is 4. Now we have identified 4 on x-axis. From 4, you draw a vertical line which is intersecting AB at F. From F, draw a horizontal line parallel to x-axis up to y-axis, and it is intersecting at point E. Now you need to get this particular point E. This is the point which you have to calculate. So you need AE value. Again, by using similar triangle property, AE by AD is equals to EF by DB. So from that, AE is equals to AD into EF by DB. The AE value is 0.198. Is it or not? So the value of this SF is, this is 0.198 and total is 2.6866. So we need to get this value, that is 2.6866 minus AE, which will becomes 2.4886. This is log 10 of SF is 2.4886. From that, SF is equals to 308.03 Newton per mm square. Once we got this SF, here the type of the stress is bending stress. So SF is equals to sigma B, that is nothing but 32 MB by pi d cube. So 32 MB with respect to critical section. With respect to this critical section, bending moment is 1000 into 150. 1000 into 150. So 32 into bending moment is 1000 into 150 divided by pi into this 308.03. So by substituting all these values and solving this, you can have D is equal to 17.05 millimeter. So in this problem, they have given number of revolutions. Corresponding to that number of revolution, you have to calculate the beam diameter. So while noting down, wherever you have S, you just note it as sigma. 0.9 sigma UT, 0.9 sigma E. So these are the problems corresponding to finite life. So whenever you have find problem corresponding to finite life, we are solving that particular problem by using SN diagram. That's the thing you have to remember. We are going to solve that problem by using SN diagram. That is the thing. In SN diagram, we have to draw a line for failure, that is AB line. In order to draw that AB line, coordinates of point A is 1000 cycles and 0.9 times of ultimate strength, and point B is 10 power 6 cycles and sigma E. You have to remember these two. If they have given life, from life we can calculate fatigue strength, or if they have given fatigue strength, from that we can get the life. So it is very, very simple. We have solved 4 or 5 problems. Maybe you have understood the process. Now let us go for problems corresponding to infinite life. These problems corresponding to infinite life are very, very simple because as already we have taken, the failure will be occurred whenever stress amplitude is reaching endurance strength. There we are getting the failure of that particular component under infinite life. So these problems are very, very simple if they are giving infinite life. The problems corresponding to finite life also very, very simple if you have understood that particular drawing of SN diagram. Now we are going for one problem corresponding to infinite life. Note down the problem. A plate made of steel 20 CH with ultimate strength of 440 Newton per mm square in hot rolled and normalized condition. In hot rolled and normalized condition as shown in figure. As shown in figure. It is subjected to a completely reversed axial load of 30 kilonewton. A completely reversed axial load of 30 kilonewton. The notch sensitivity factor can be taken as 0.8 and expected reliability is 90%. Expected reliability is 90%. Size factor is 0.85. Factor of safety is 2. Determine the plate thickness for infinite life. Take surface finish factor as 0.67 and theoretical stress concentration factor as 2.51. So this is the plate, a plate of 50 mm width and a hole of 10 mm diameter is made at the center, and you need to calculate the thickness of the plate. So load is 30 kg plus or minus 30 kilonewton. This is completely reversed load is acting on that, and the material whichever may be used is steel with ultimate strength of 440 Newton per mm square. So this is the data given for us. So first we are calculating theoretical endurance strength, that is 0.5 times of sigma ut. So it is 220 Newton per mm square. And reliability factor for 90% reliability factor is 0.897. Already size factor is given as 0.85 and surface factor is 0.67. Now we are calculating fatigue stress concentration factor based on notch sensitivity and theoretical stress concentration factor. So Kf is equals to 1 plus Q into Kt minus 1, which will be 2.208. From that we are calculating modifying factor, which is nothing but 1 by Kf, that is 0.4529. From all these factors, here one more thing is there, load factor. So for whichever may be the problems we have discussed, We have taken load factor as 1 because the actual conditions and laboratory conditions are same. Both are bending only. But here, the type of the load is axial load. So we have to consider the load factor, that is 0.8. Now we are going for corrected endurance strength. So sigma E dash is multiplied with surface factor, size factor, modifying factor, load factor, and reliability factor. So by multiplying these 220 with all these factors, we are getting corrected endurance strength as 40.72 Newton per mm square. Here there is no necessity to plot SN diagram. SN diagram will come into the picture only for finite life problems. Here we don't need that particular SN diagram. So we are calculating stress amplitude. That stress amplitude equals to corrected strength, corrected endurance strength by factor of safety. That is 40.72 by 2, which becomes 20.36. Then we are calculating plate thickness. So whatever maybe the plate is there for that particular plate, we have stress amplitude is load by area. Load is 30 kilonewton and area is total width is W. In that particular plate, we know that this is the critical section. Wherever we have the weaker portion, that is considered as critical section. So with respect to this critical section, this width is total width minus diameter, W minus D into thickness will give us area. So the stress amplitude for that plate is P divided by W minus D into G. So P is 30,000, W is 50, D is 10 into T. So this is the stress amplitude based on the properties of the material. This is stress amplitude based on the dimensions. So in order to avoid the failure, these two should be same. That's why we are equating these two. By equating these two, 20.36 with this, we have only one unknown, that is nothing but thickness of the plate. So you substitute, you are taking stress amplitude from the properties at one side, stress amplitude based on the dimensions, because whatever may be the load acting on that, that should be taken by the material. So the material is having, this is the area. So by equating these two, we can have the thickness of the plate is 36.84 millimeters. This is the problem with respect to infinite life. Remember a thing, whenever we are solving the problems with respect to infinite life, there is no need to consider SN diagram. Only we are considering the stress amplitude. So we have two more problems. If possible, you note down those two problems and try to solve at your home. Or at least you solve this one problem. A rod of a linkage mechanism made of steel 40Cr1, this is the alloy steel, with ultimate strength of 550 Newton per mm square, is subjected to a completely reversed axial load of 100 kilonewton. The rod is machined on a lathe and the expected reliability is 95%. There is no stress concentration. Determine the diameter of rod using a factor of safety of 2 for an infinite life condition. So surface factor is 0.78. This is the problem given. Only you note down this problem and try to solve it at your home. Actually, I thought to finish this problem, and I have prepared one more problem for homework, but this problem is also not completed. So you take this as the homework problem, and let us discuss the other problem tomorrow, sorry. You take this problem for homework. Very, very simple problem. You need to get the corrected endurance strength. From corrected endurance strength, you need to calculate allowable strength. That allowable strength will be equated with resistance offered by particular machine member. Then you can get the unknown diameter of that shaft. So you make an attempt at your home. This is the problem for homework.